So there's this trend where machinists love to optimize this stuff, the stuff happening in the machine and the stuff immediately around the machine. Tool organization, work holding, etc. We make process bins. We organize our materials and make Kanban cards. We reorganize our shop 6 different times so everything's within arm's reach of the machine. But then when we get a PO and we actually have a part that we need to program, we have 0 optimizations. Most machinists start from scratch for every program for every part. That's like the equivalent of remachining a fixture like this every time you need it, and then when you're done with it, just throwing it away. It's stupid and wasteful. So allow me to introduce you to the wonderful world of Fusion CAM template documents. So this over here is my part that I want to machine. So I'm gonna drop this in here under this component called container. It's going to drop in right at the right place. I'm going to take this component called delete me and I'm going to remove it. So there's my component there. So now I can come back and open my parameters menu and adjust my stock size. So let's say 4.5 by 3.5. And it's looking a little bit too thick. So let's make that 0.5. Yep, that should do nicely. Now I can go into the CAM workspace. Future AJ here. I have been editing this video for about 2 hours, and as I have been editing it, I have realized that a lot of the stuff I'm covering is pretty advanced, and I'm covering it at a fast pace. If you are new to Fusion, I would not expect you to be able to keep up with this video or understand most of the stuff that I'm talking about. This video is very much for advanced users who are already familiar with making parts in CAM. If that doesn't describe you, feel free to continue watching it. I'm sure you'll learn something. But don't be discouraged if this moves a little bit too fast for you. And if you're just here to see me make things, this is not going to be my typical kind of video. I'm going to get deeply technical and nerdy into stuff that's probably boring for you. Now that my retention and view count is shot, I'm going to get back into computer mode. I'm going to start by regenerating all of my toolpaths. Now we can go through my toolpaths. Okay, this one looks like it did a pretty good job of roughing out. This toolpath doesn't look super necessary, so we'll delete that. Apparently, I am incapable of recording stuff out of order and making it make sense when I go to actually edit it together. So here's what is happening right now. I'm gonna overlay some of this footage. The idea behind these templates is that you have all of your toolpaths pre-made in an existing template document that you can just copy and paste. When you're ready to make a part, you just copy your part in, paste it inside the correct container, and then regenerate all of your toolpaths. Those toolpaths, if designed correctly, as much as possible, they should automatically pick up on the various geometries of your part automatically without any need for human interaction. Now there's limitations to some of the things that Fusion allows, and so it does require some human interaction, and it's also generally better to have too many toolpath templates instead of too few. So what I'm about to do is I'm about to go through all of those templates that I just regenerated. I'm going to delete out the ones that we just don't need. I'm going to fix the ones that don't make sense, and I'm going to make a handful of selections on the toolpaths that need selections. So I'm just going to get rid of that toolpath. So with that done, we could right now start this running. We could put this on the machine, hit go. I have to change my tool numbers. But with just a few seconds of work, we could be making chips. And this gives us about 10 minutes where we can now program the rest of the part. So I'm gonna look back in the video and time how long this whole thing took. But the amount of time that the part was waiting on CAM was this long. There will be more time that I'm doing CAM, but the part only waited for whatever this number is right here. So let me clarify this a little bit more. If you are trying to do short-term work, what matters is how long it takes your part to get out the door. If your part is waiting on CAM, it is not on the machine getting closer to shipping. But you don't need to have all of your CAM done before you put it on the machine. If you have good processes and proven speeds and feeds, you can throw your part onto the machine and do the bulk of the material removal while you're still finishing the rest of the program. And sure, the first thing you post out is not going to be super optimized, but a spindle that's making chips is far more optimized than a spindle that's not making chips. You'll have time to go back and optimize this program while it's running the finishing operations. So now that the machine's running, we can take our time on the rest of it. We'll start with contours. That one looks good. That one looks good. That one does nothing. Get rid of that one. So this goes on for about another 5 minutes. Basically, I'm just continuing to tweak the finishing tool paths. I need to remove some, I need to add some, I need to fix a tool length, and then it's good to post. You will see the details of all of those tool paths when we actually make our template in a second here. But the important thing is this took about 5 minutes. And so our total cam time on this part is about 8 minutes, with about 4 of those minutes being while the machine is already running. For this part, those 4 minutes may not be worth the effort of getting the machine started earlier, but if you're running more complicated parts or parts in something like stainless, you could easily have 20, 25 minutes, half an hour of roughing. 3 different threads, a bunch of different features, and it just took a couple minutes to cam. This is why tool templates are so powerful. So now that you've seen what these toolpath templates can do, let's go back in time to when I originally built this template. I'll walk you through all of the steps on how to get here. Before we get too far into things, I do want to say that I am very much standing on the shoulders of giants. There are people who have gone before me who are much more intelligent and have pioneered this idea. Specifically, this concept comes from a talk that Rob Lockwood did at Autodesk University. I will link that original talk down below. Since then, Fusion has come a long way, and I've kind of built on top of his original talk, though I would suspect Rob is already way beyond what I am doing here. So thanks, Rob, for sharing your original idea and teaching us. It has, I think, helped the whole industry move forwards, and I hope I can add just a little bit of something on top of what he already taught us. And I hope that my own implementation can move us just a little bit further along. So let's look at making one of these templates. Now, the first thing I like to do, though technically this isn't necessary, but the first thing I like to do is to make a part that kind of looks like the parts that I'm making the template for. In this case, I am making a template for flat parts that I'm going to make with the super glue method. I did a video on that method recently, and I've been using it a ton over the past couple of weeks, and I just need a better workflow for it. So that's what we're going to build today, my actual template that I'll actually use. If you look here at my little sample part, I have a bunch of different pockets of different depths and different corner radiuses. I have a couple different little bosses here that have different deburring treatments. This one has a modeled fillet, this one has a modeled chamfer, and this one does not have a modeled chamfer. Though of course we'll deburr our edges. Then I have some holes of different sizes here. These are just bores, whereas these here are set up as tap holes. If I remember right, this starts at like 80 and then goes up to, I think it's quarter 20. No, bigger than quarter 20. I think it's 3/8 16. Then I also have some slots. And lastly, I have some little things that we can do some surfacing on. So first we need to set up our components correctly. So this is called the container method for a reason. And that is because we need a container component. So I'm going to make a new component, and I'm going to label this one container. And then I'm going to move the body I made into that container. And lastly, I'm going to rename our body, delete me. Because this model is just temporary, and as soon as you start doing your cam, you'll delete this out. Let me do a better job of explaining this container component. By having a top-level container that you put your actual machine part inside as a subcomponent, you keep Fusion from getting confused by swapping around the models. If you didn't have that top-level container, when you replace the model, Fusion would get confused about where to generate the stock and where your work coordinate system is and what actual model you're machining. But by selecting that top-level container in your setup, it automatically includes all of the subcomponents. And you can swap around the subcomponents and they will automatically be included in your setup. Despite being the namesake of this method, it's not actually a huge deal. It just saves you a couple minutes of confusion when you're first getting into the document. So next we need to set up our stock, which I am not going to reference off of anything except the origins. And I will do is a center rectangle. And I'll use parameters to call this stock X, and let's call that, I think 6 inches covers our template. And this will be stock Y, and 4 inches should be good in that direction. Then we can extrude that by stock Z, and let's call it an inch. I don't remember what my existing model is. let's make this glass so that it's nice and opaque. And then lastly, we need to rename this stock. Now we could put this in its own component, but I don't think it matters. And since we set it up parametrically, in the future, if we need to change it, like when you're modeling your part, for example, you can come into the parameter menu and just change whatever dimensions you like. So now with our stock set up, we can go back into the manufacturing environment and set up our setup. So I'm going to start with the stock here, and I'm going to set it to from solid. And then over here on the tree, I'm going to choose my stock. Then under the setup tab for the model, I'm going to choose, and you have to be careful which you choose here. I'm not choosing the delete me body. I'm choosing the container component. So I'm going to choose the container component as our model. And in this case, I'm not modeling in a fixture, but in the majority of my templates, I do. If you are doing that, of course, here is your chance to select your fixture. And if you use any standard work coordinate systems for your fixtures, this is where you put them in. So I'm going to rename this setup op1. And now we can start doing our actual cam. Our goal with all of these different operations that we're going to put into cam is to make them as automated as possible. All I want to do is hit generate. I don't want to have to select anything if I can avoid it in any way. This is easier for some of the tool paths than it is on other ones. The easiest one to automate is bore. And in fact, if you've ever watched any of my videos, you may notice I almost never use drills. And that's because I have everything automated with the bore tool path. So I'm going to come in here to my tool library. We'll set this template up for aluminum, but once we're done with it, we'll just duplicate the whole template and change my tools over to my harder material tools. But for now, we will do my aluminum tools. And I'm just going to start with my 1/32 inch end mill and choose the right tool preset. And on the geometry tab, instead of selected faces, I'm going to go to diameter range. So our minimum diameter is going to be tool underscore diameter times 1.2. And our maximum diameter is going to be tool underscore diameter times 2. So anything that is between 1.2 tool diameters and 2 tool diameters is going to get bored with this operation. Now, unfortunately, bore is not smart enough to understand if the tool is long enough to make the hole that it is, like, boring. One thing I can do now, I'm going to change where it says hole top, and I'm going to make that model top. In this case, it's just adding extra cycle time, and you could go tweak this when you're actually doing your CAM programming, but this is a safety measure. One, because sometimes there may be material on top of the hole that you need to bore through before boring your hole. And secondly, because sometimes you have a modeled chamfer or fillet on the edge of your hole, and if you have this set to hole top, it will just crash through that extra material before starting the boring operation. So by default, having this set to model top or even stock top is safer. Now, unfortunately, bore doesn't have any tools to check to see if the tool can actually reach the bottom of the hole. So you always need to make sure that you hit simulate when you're programming your actual part. But this would be the good time to set any other tool settings that you would like. For example, if you want to repeat passes or not, or if you want to do in-control compensation. I do not do that on a tool this small. But once you are happy with all of your settings, you can hit OK and then duplicate that bore tool path. And now all we need to do is change out the tool. So that was a 1/32 inch end mill. Now I'm going to go to my 1/16 inch end mill. And if I've set everything up right, I shouldn't have to make any changes. It should just automatically pick up on the correct holes for it. Let's do that again for our 1/8 inch end mill. 3/16 and 1/4 inch. Select that. 1/4 inch is actually the biggest tool that I consider to be a core tool. It's like the biggest tool that I'll keep set up in the machine out there. I make really small stuff, so there's no need for me to go bigger than that. Obviously, tune this for whatever makes sense for the kind of work that you do. I would be shocked if most of you guys are boring holes with 1/32 inch end mills. That's kind of a me thing. And I would be surprised if most of you didn't have something like a 1/2 inch or a 3/8 inch end mill in here. To keep things organized, you can now make a folder, and we're going to call this boring. And I'm going to put all of my boring toolpaths in there. So now when you're actually using this CAM template, you can just come in here, look at all the boring ones. If there's any of these that are reading 0, you can just delete them out. Or if there's any that you need to change, you'll know right where to find them. Now, I'd like to point out, these grabbed most of our holes right here, though they did miss a couple. These ones just happened to be at the right sizes, or the wrong sizes, I should say. We didn't have a tool that was big enough to get them without adding multiple passes, and we didn't have a tool that was small enough to get them without basically just plunging into the part. So again, you may have to go back and do some revision based on what your part happens to look like. But the fact that this will cover the vast majority of hole sizes for 0 effort is really nice. I started with the boring operations because it was kind of an easy way to illustrate some of these principles in how we're going to set up these templates. But really, there's no reason why we should ever start any of these parts with anything other than a roughing operation. So we'll rearrange these things when we're done, but we can move on to setting up some adaptive toolpath. I'm going to start with my biggest tool and then move smaller. So again, I'm just selecting my correct tool and preset. For setting up this roughing, there's a couple things you can do in your heights tab. Because I'm using the super glue method on this one, I'm just going to do model bottom, and I'm going to go down 0.01 inches. And that is because in this case, I am using a sacrificial fixture that I want to make sure that my tool is cutting all the way through the part and there's no onion skins or anything left. If you were doing something like a vise, you could just go to selection, click on the top of your vise, and type in, however much you feel safe with, something like 50 thou. And that way, no matter what happens, no matter how your part's situated, you will always be 50 thou above the top of your vise. For stock to leave, I'm going to leave myself 5 thou stock to leave, so it's actually only cutting 5 thou done. And again, this is a good time where you can set up whatever other settings that you like for your roughing operations. Now, when you are setting up these adapters, one very important thing is to turn on the shaft and holder detection. This will just make sure that it's not going to try to cut too deep or too close to some other feature and crash your tool holder into your part. So I like to use it in this pull away mode, and the clearances that are about shown here. 0.02 may be a little bit high on the shaft. We can go down to 0.01. And just like before, we will add those to a new folder called roughing. We'll put our toolpaths in it, put it above our boring, and get rid of our typo again. The next toolpath we're about to do is honestly my favorite toolpath in all of Fusion, and that is flat. Flat can do both floor finishing and it can finish the walls of pockets. The problem with flat is you can't turn on tool diameter compensation, or wear comp. So in this case, besides all the normal stuff to get the toolpath to look however you normally like it to look, I'm going to give it no axial stock to leave, and let's do 5 thou radial stock to. Just like with adaptive, we need to turn on the shaft and holder section, which again, I'm going to go with the pull away setting and give it a clearance of 10 thou. And just like before, we now need to duplicate this a whole bunch of times and choose our various appropriate tools. Just going down our standard core tools. Now you may notice some of these toolpaths are just nuts. You would never ever actually run a toolpath like this, or really even like this one. But that's okay, because on some parts, these toolpaths will make sense. When I'm actually programming a part, I would just look at these and delete them and then move on. It's okay. There's going to be some extra toolpaths here that are ugly or that just don't work, and that's okay. The next toolpath we're going to do is a 2D contour. And to make this one intelligent, we're going to have to do a little bit more shenanigans. So this time, if we come over here to contour selection, we have a couple different options. The first thing we're going to do is we're going to finish the outside walls of the part. So I'm going to hit this button here, it's silhouette, and I am just going to select outer loops. So now, regardless of whatever part we throw in here, it will always just select these outer loops. And on here, I'm going to do my bottom height back at 0.01 inches. And I'm going to do in control compensation for how I do this stuff. And again, from here, it's however you normally set up your toolpaths. You can turn on roughing passes or whatever your traditional SOPs are. Except this time, I'm only going to do the one toolpath. I'm not going to do multiples because chances are you're basically just going to be doing this with like your biggest tool or with a finishing tool. But for me, I do the majority of my work with this 3/16 inch 3 flute. So that one's simple enough. Now we need to do the inside of these pockets here. And this time we're going to click on this little drop down button here. And you notice there's a bunch of options that you probably have never noticed before. One of those is pocket recognition. For bodies, we don't need to select anything as long as this checkbox is checked. We do need to adjust our corner radiuses. Now, unfortunately here, we cannot just type in tool diameter. It, for some reason, does not work in this menu. So I'm going to have to go in and manually set all of my tool diameters. So in this case, it's a 1/4 inch tool. So I'm going to do 1/4 inch divided by 2. The maximum quarter radius doesn't matter. So I'm just going to make it a really big number. Minimum depth, again, doesn't matter. For the maximum depth, again, unfortunately, I can't type in flute length. So I'm going to have to type in the actual amount, which I know is 0.75. Now you can click this include holes button, and that includes holes like this, but we have already machined those, so we don't need to in this case. So you can see here, it automatically identified this pocket, which is the only one that is accessible to the 1/4 inch tool. And now I get to just duplicate this and manually update my numbers to get all of these other pockets with all of the other holes. Now, unfortunately, we are at the part of the day where we have to make a manual selection. So far, everything we've done will automatically populate, and all we'll have to do is delete existing toolpaths. But to finish these walls here, we could do it with a flat, but if we did it with the flat, then we wouldn't be able to come back and do cutter compensation on the walls of these pockets here. So unfortunately, the easy way is to set this up with a regular 2D contour. I'm just going to select a tool here. You may need to change this when you're actually making the part, and I'm going to manually select these contours. And unfortunately, that means this contour here will not be automatic. It'll not be intelligent. If you have any bosses like this, then you'll have to manually select them. I should probably turn on the in control compensation, which is the whole reason this toolpath exists. The only other thing I'm going to do here is I'm going to, do 0 radial stock to leave, and I'm going to give it 5/10 axial, just so it doesn't do anything weird on our floor in case there is a height mismatch between whatever tool we finish the floor on and whatever tool we finish the wall with. So looking at our toolpaths here, we are roughed out, we have the floors finished, we have holes done, and we have pockets and bosses. So that leaves us with threads, with slots, and with things that need to be surfaced in. The next step here is the slots. I'm going to use the standard slotting tool, but unfortunately this is another one of those cases where there just is not an intelligent tool to select it for you. So in this case, I'm just going to have to manually select the profile. And when you're actually making your part, you're just going to have to manually select everything. And toolpaths like this are a good example of something that is technically set up correctly in our template. But man, if you were ever actually running this, you would want to go manually change the top height to be something a little bit more reasonable. Even that is still a whole lot of unreasonable. So I should change this ramp clearance height on all of these. It is now time for the thing I've been avoiding, and that is threaded holes.
I generally avoid taps if at all possible, so instead I thread mill everything. Setting up these automatic thread milling operations is going to be really similar to setting up the bores, except this time we're going to choose the thread mill toolpath, and we're going to have to be a little bit more specific on our diameter ranges. So if we go over here to my spreadsheet, we're going to start with the aught80 holes. See, the right thread mill was already selected, so there is our tap hole diameter, our pitch, and our pitch diameter offset. For this minimum diameter, I'm going to go a few thou below whatever this says. So this is 0.049. So 0.049. I'm going to go minus 0.002. And then for the maximum diameter, I'm going to go plus. That way, if it was modeled just a little bit differently or with a different thread engagement setting, it should still automatically catch it. And then, of course, I now need to add the pitch and the pitch diameter offset to my toolpath. So the pitch is 0.0125. And my pitch diameter offset is 0.0144. And then just like with the boring operation, I'm going to change the top height from hole top to model top, just to avoid any weirdnesses if there is a modeled chamfer. And then for the bottom height, I'm going to give it just a little bit of clearance, just so that if there's any chips in the bottom of the hole, if there's any height mismatches, or if there's a little bit of a drill cone. But that should be good, and now we can begin the very long task of duplicating this. I finished up doing all of the imperial threads at very least and put them in their own little folder here. I'll come back later and add the metric threads, but frankly at this point I'm really tired of threads and I want to move on to something else. Deburring can get complicated only because there's so many different options for how a customer may want things deburred or by how it may be modeled. You can have a modeled fillet, you can have a modeled chamfer, or you may need to do an edge break that is not modeled. So a better way of doing these modeled chamfers is just to use a 2D contour, grab a chamfer tool, and then coming over here to the passes tab, turning on chamfer mode, and I'm going to give it a little bit of a tip offset, but a 0 chamfer width since I am going on a modeled chamfer here. If you were doing this with a chamfer that wasn't modeled, that is when you would turn on this chamfer width option. Then, of course, I need to rename this. So this is going to be modeled chamfer. Unfortunately, I have not been able to find a way of automating this, so you'll just have to manually select these. So that's the modeled chamfer. Now we need to do the unmodeled chamfer, which works exactly as you would suspect. Again, there is no way of automating this. I've experimented before trying to do pocket recognition or using like the silhouette of the part, but honestly, these methods cause more trouble than they solve, so it's best just to manually select what you want to have chamfered. And again, we're going to rename this unmodeled chamfers. And on these ones, you just have to go in and manually select what chamfers you want every single time. And then lastly, we need to do our modeled fillets here. And for this, I'm going to do a blend and select my surfaces. Yet again, we have no automations for this. I've done this before with a 2D contour, but it does not give me reliable results and tends to cause more problems than it does good. So we'll select our ball mill with the correct speeds and feeds again. And step over should be good. And that'll give us a nice surfacing tool path on this fillet. So this is going to be fillets. When you're doing your actual cam, you will have to duplicate this and then remake all of your selections every single time. Before we move on to surfacing, I would like to point out one more thing, and that is this deburr toolpath. If you have the manufacturing extension, this deburr toolpath is really good at automatically picking up a lot of this deburring stuff without any human intervention. Surfacing gets tricky because there are so many different possible geometries that you may need to finish in different ways with different tools and different methods. So out of everything here, this is definitely going to be the least of the one-size-fits-all tool paths here. but there are some things that we can do to get you a better shot of getting something that works. Now, contour is one of my favorite surfacing toolpaths. It works best on steeper walls. So we're going to turn on the slope setting here, and we're going to go from, let's call it 45, that may be too shallow, to 90 degrees. And that'll get like the steep sections of the walls here while leaving the shallower sections. And let's go back and change our step down height. So as you can see with our current settings, the contour likes to pick up on vertical walls. That's not what I intended, because our vertical wall should already be finished with a regular 2D contour. So let's change our slope angle here to 89.9 degrees. And that should rule out anything that is straight vertical. But you can see the problem with contour, it likes to grab parts of these sharp corners. So you will have to go, when you're actually programming this part, and do something like setting a tool boundary. And that should, just isolate to whatever you want to do. But with our slope settings, there's obviously some parts of this that we're not machining. And that is where our next toolpath comes into play, which is scallop. Now for scallop, I'm also going to turn on slope, but instead of going from 45 to 90, I'm going to go from 0.001 to, let's call it 50 degrees. So there's a little bit of overlap. We'll change our settings, okay? And this should grab everything that the ramping toolpath missed, or the contour toolpath missed. So this is getting those walls there, and then the scallop here is getting the floor. Essentially what we've done is we've recreated the steep and shallow toolpath, which requires the manufacturing extension. Though, again, scallop has grabbed all kinds of random stuff that we don't want it to grab. So when you're actually programming your part, you're going to want to set a boundary to kind of keep it contained to where you want it. But between those toolpaths, we should get a lot of our surfacing covered. And then lastly, there is one more toolpath that is frankly just magical, and that is this geodesic toolpath. Geodesic, you do have to manually select things, but once you select them, it does a pretty good job of giving you a pretty good toolpath without much effort. Just need to change my step over settings, select machine over holes in case that comes up, and this should give us something pretty decent. So I'm just going to leave that toolpath set up there so that we can easily copy paste it for whatever various feature we need to machine later. So now I need to take a step back and kind of look at the process I use and build some of those process steps into this template. Now, I have a whole YouTube video on the superglue method. You should probably go watch that for this to make the most sense. But a lot of the times when I am doing these superglue parts, I am doing them as essentially a one-op part. Most of the time, I start by facing the backside of the material, and then I glue that clean-faced material down directly to the fixture. And the fixture, I again face right before I put the material down. So I'm starting with a finished edge on the bottom here, and I'm starting with a finished edge on the top of the fixture. The top of that fixture is what we want as our 0 point, because that is where the two edges are mating. So I'm going to go back to this original setup, and I'm going to change the 0 point here to be at the bottom. So right there, that's where I want our work coordinate system. But picking up the middle of a block is kind of annoying. So to make that easier, I'm going to come and add another toolpath here, and I'm going to add a probing cycle to pick up the center of our stock. In this case, because the stock is modeled, I'm going to have to pick model instead of stock. I can click the top there and set my heights down a little bit, select my probe, and move this to the beginning. When I run this program, I just kind of have to have the material roughly centered. I just need to know roughly where my XY position is, and the probe will do the fine-tune dialing in on its own. Now notice I am only setting the XY position. I am not setting the Z position with this probing, because we will already know exactly where our Z position is from our fixture. And that fixture is the next thing we need to do. So for the fixture, I'm just going to duplicate my same setup here. I'm going to get rid of all of my toolpaths. And basically that just guarantees that our work coordinate system is in exactly the same place. That's why I did that. Then I'm going to open up the setup. I'm going to remove this model and I'm going to make the stock our only model. And then I'm going to make a facing toolpath that is going to deck off the top of our fixture. So we'll do that with my 1/4 inch. I'm just going to use my roughing speeds and feeds. And this time I'm going to do it as the model bottom. Give it a reasonable step over. No pass extension, but I'm going to do a stock offset of the tool diameter. And there we go. This will face off the base of the fixture right below the part. So there's the part. Here is our tool path that is going to make the fixture. Obviously, you want to do this before gluing the part down. And because this tool path is directly on our work coordinate system, we'll know that that surface of the fixture is right where we want the bottom of our part. So remember when I said that most of the time when I do this, I face off the bottom of my material before I get started? We need that operation now. And it's actually almost identical to this fixture decking, but with a couple little mild changes. I'm going to duplicate this. I'm going to call this op 0. And then I'm going to come set my work coordinate system to be right on the top here and still centered. I'm going to go grab my probing operation from up here and paste that in. Put it in the right order, make sure it's still selected correctly. And this time, my face height here is going to be model top minus 0.01. So basically, that'll just take 10 thou off the top of my stock. And on this one, I do want the probe to set my Z height. So I'm going to make another probe and this time do the top. And I will set this up here. So now it'll probe the top. It'll make sure that it's centered and it'll face 10 thou off the top. So that was like a lot of work to get set up. This took me a couple hours to record the CAD portion of this video. But now, whenever I run a super glue fixture part, I just drop the model into this, I regenerate my tool paths, I fix what's dumb, I add what's missing, and I hit post. Again, it won't cover everything I do, but it'll cover most of the tool paths for most of the parts I make, and that saves me a huge amount of time. Now we just have one last tweak that I want to make to our tool paths, and that's solely just an organizational thing. I'm going to make a new folder here, and we're going to label this one Start Now, with lack of a better word. We're going to make a new folder, and we're going to call this one Start Later. Now, some of these tool paths, like the probing, the roughing, and the flat tool paths, those tend to be very safe. You can do just a quick simulation, and if that simulation's good, you can hit go before everything else is programmed. So I'm going to move that folder up to the top here. These other tool paths, they need a little bit more babysitting. They take a little bit more time. And so I'm going to put those in the Start Later folder. What this means is when you're programming a part, you can drop your model into the template. You can hit generate. You can post the Start Now stuff, go set up the machine, hit go on the machine where it's running those Start Nows and only the Start Now stuff. And then while it's running those first couple tool paths, you can start the Start Later stuffs. So that way you can keep programming the part while the part is running. Now tasks are parallelized instead of being serialized, which means you can get your part done faster. You can have a part that takes an hour to program and an hour to run, and you can get it done in less than 2 hours. And don't get me wrong, that's an advanced thing. You have to be safe when you're doing that, and some sort of whole machine simulation would be helpful. And you really need to have your speeds and feeds dialed in so that you can trust everything to just run. But once you get to that point, you can do things so much faster than anybody else. People wonder how I can make money on Xometry being so slow at actually running the machine. This is how. Because I can be programming the part while the part is running. It also means that I can look for jobs on the Xometry job board that fit inside my template and use my standard tools. And I can run 3 or 4 of them in a row, but without any setup time. I just put them on the machine and I hit go and I end up with a finished part. And yeah, sometimes I have to go back and make little tweaks. Sometimes there's features I missed or I need to dial in a bore or whatever. But having these templates set up really saves a ton of time and effort.